This meeting is being recorded.
In problem number 29 from chapter 9, we're asked to propose an efficient synthesis for each of these transformations. So that would mean that if we know multiple ways of performing this transformation, we would end up choosing the one with the least number of steps. So the most efficient synthesis would have the least number of steps. So that's what I have shown here for A through D for this problem. So in A here, first we can use our base, our sodium amide, and we can add this carbon that has been added to our carbon skeleton with a methyl iodide alkyl halide. So we can add that, and then we also need to produce a trans-alkene. So we can accomplish that from our, we'll have added on that methyl group. So we can perform a dissolving metal reaction and end up with our trans-alkene product. So this would be the most efficient synthesis to go from our starting terminal alkene, or alkyne rather, to a trans-alkene product. Next we have an alkene, and we would like to create this alkyne product. So what did we do here? We have added onto the carbon skeleton. So what we've done is we've halogenated our alkene. So we end up with this racemic mixture after step 1. And then we perform an elimination, or actually 2 eliminations. So we would have excess of this, and then use water to form a terminal alkyne here. And then in this next step, actually steps 4 and 5 together, we would add on this methyl substituent here with sodium amide and then methyl iodide. So for reaction C, or transformation C, we could first reduce this triple bond to a alkene double bond using H2, molecular hydrogen, and Lindlar's catalyst. So we'll stop at an alkene. And then we can use dilute sulfuric acid to have Markovnikov addition of H and OH on our double bond, and we would form this alcohol product. In our last transformation, D, we see again a terminal alkyne, the same as with reaction A and C. And we treat this first with molecular hydrogen and Lindlar's catalyst. So we end up with our alkene product. And then we want to have anti-Markovnikov addition of H and OH across our pi bond. So we would use hydroboration oxidation here to have the most efficient synthesis. And by using that with steps 2 and 3, we get this anti-Markovnikov addition of OH and the alcohol product that we're looking for.